All right, so in this video, we're going to derive the D2 character table. And the best way to start out with a lot of these character table derivations is to first envision a molecule that lies in this point group. This is a tricky task for the chiral point groups. D2, the DN and the CNs are chirals. So it's best, I'll show you an example here of a molecule that does have D2 symmetry. But basically here, in these chiral point groups, there's not a lot of different symmetry operations. So you can kind of just list them without really visualizing a specific molecule. That's not really required. You can think of D2 as just like D2H, except it doesn't have any mirror planes. And so and you have to know some rules of the D point groups. Remember that D point groups always have D point groups, right? They will always have n perpendicular C2s. So if we are Dn, right? So if we're D2 in this case, that means that there's going to be a principal rotation axis, which is a C2. And we always we define that as the z-axis. So that's the principal rotation axis. And then in addition to that, we're always going to have n perpendicular C2s. So we're going to have a perpendicular one, we could call that C2x, and also C2y. Those are the two additional perpendicular C2s. So D3 would have a C3 for principal rotation axis, and it would have three perpendicular C2s. So very quickly we can come up with what these principal rotation, these different symmetry elements would be. Basically, we've written the three symmetry elements that there are, and we just need identity. So these are the four symmetry operations in D2 symmetry. And in this case, they're all in four separate classes. We know that identity is always in its own class, so that one's easy to figure out. And then it's a little bit more tricky, but thinking about these C2s, in the DN or the CN point groups, your rotations are always going to be in separate classes when they're on different axes. And the reason for that is because the definition for whether or not two symmetry operations should be in the same class is that there's some arbitrariness in the axis system that you use to define the operations. And if there is, that you can interconvert between two symmetry operations that would make the two operations in question that you can interconvert between those two Cartesian axes with some other symmetry element in the point group. So for example, we know that when we're going through this, we always define our principal rotation axis as z. So we could define that here, doing a C2 this way. That's going to be our principal rotation axis. We're required kind of by how the character tables are constructed to define that as z. Otherwise, we'd have a different character table with different values. But the x and y are arbitrary. And so we could think about, this being the x in red, right? And thinking about in blue, this being the y, this C2 being the y. And you could say, well, we can just flip these. We could call this y and this x. And yes, that's true. But there's no way to interconvert between an axis system that looks like this, between those two axis systems. Sorry, I should have used green there for clarity. There's no way to interconvert between these two axis systems using symmetry operations. That is, if we do the identity on one of these axis systems, it doesn't get us to here. If we do any of these C2s to this axis system, it doesn't get there. And that is the mathematically rigorous definition of why these have to be in different classes. If you're asked to derive these character tables, the fastest way is just to look at patterns. So I would just look through all the character tables and know, hey, with the D point groups, if I'm talking about axes, the Dn point groups axes, rotation axes that are on rotations that are on different axes, like Cx or C2x or C2y, that those have to be in separate classes. Okay, for this reason. All right. So with that, we can now write out our kind of skeleton for the character table. So to do this, we, by convention, always write the point group of the character table on the top left. And identity is in a class by itself. And then we have the C2Z, and we could do C2X and C2Y. So we have 4 different classes. Each class only has one symmetry operation. And so then we're going to put placeholders for our irreducible representations. We know we're going to have 4 of them because that's one of our character table rules, that the number of rows has to equal the number of columns. We don't know what the Mulliken symbols are for these until we come up with the vectors, the irreducible representations. But we do know we'll be able to do that at the end. But we do know that the first irreducible representation is always ones across the board. And at this point, we know another rule, which is the sum of the squares of the dimensionality, that is the character that's underneath the identity in this first column, has to be equal to the order of the point group, which is the number of operations in the point group, which is 4, right? 1 plus 1 plus 1 plus 1. There's invisible 1 coefficients here in front of all of these. So we know that 1 squared plus, we could call it A, B, C here, we don't know what they are, plus A squared plus B squared plus C squared is going to have to equal to 4, the number of symmetry operations in the point group. And the only way to have valid solutions for these, they have to be whole numbers. They're going to be 1, 2, 3. In very rare cases, like high order point groups, they're going to be 4 and 5, but usually just 1s and 2s, and sometimes 3s. The only way to solve this is that A, B, and C all have to equal to 1, right? 1 squared plus 1 squared plus 1 squared plus 1 squared equals 1. So now we can erase our ABC there and put in 1s. And at this point, it actually, we can use one more rule to just come up with our final table here pretty quickly. And that is that we have to be orthogonal. And so all these vectors, gamma 1, the dot product of any 2 vectors has to equal to 0. That's what orthogonality means. In mathematics, they're perpendicular to one another. And it has to be normalized. This orthogonality has to be take into account the number of operations in each class. Well, the number of operations in each class is 1. So we know we have our first vector, which is 1, 1, 1, 1. That's gamma 1. And our second vector is 1. Now we can call it, I don't know, let's not use X. Let's use DEF. 1 comma D comma E comma F. That has to be equal to 0. And what I meant earlier by it has to take into account the number of operations in each class. There's 1 operation in each class. So there's invisible 1s here. And so if there's a 2 there, we'd have to multiply by 2, but there's 1. So all of these, we have to take one of the vector and multiply it by 1. It doesn't change anything in this case because they're all 1s, but just to be rigorous. And so at this point, in order for this to be equal to 0, I think you can pretty quickly see that you're going to need in the case when you have ones, you're always going to have negative ones or ones also. So whenever your dimensionality is 1 here, the character table forces your other characters to be ones or negative ones. And so if D, E, and F are forced to be 1 or negative 1, you're going to need one of these letters to be a positive 1 and the other 2 to be negative. So we could do it like this, right? Because then when we dot it, we're going to get 1 dotted with 1. 1 times 1 is 1, plus 1 times 1 is 2, plus negative 1 times 1 is negative 1. That gets us down to negative 1, and then another negative 1. So these times 1. So we get negative 2 on this side and 2's on this side. That gets us a total of 0, right? So if we dot this, now if we sub in what we put in here, this is a true expression. And basically it's going to say, if we simplify this just to have all ones here, is this true? Just for clarity, this is true, right? So we multiply the first terms, 1 times 1. This is the definition of the dot product. Second term, 1 times 1. Third term, 1 times negative 1. And fourth terms, 1 times negative 1. And that all indeed does equal 0. But, it's arbitrary where we put our 2 negative 1s. So we could do it like this, or we could do it like this. Those are the 2 other permutations, and all those are valid, and all those are going to be orthogonal to one another. And we can also check, it's not that that ensured by our logic that they're all in gamma 2, gamma 3, gamma 4 are all orthogonal to gamma 1, but they're all also going to be, all the other permutations or combinations are going to be orthogonal as well. So we could think about, for example, gamma 3 dotted with gamma 4. In that case, we have 1 times 1 plus negative 1 times negative 1. That gets us up to 2. But then these 2 are 1 times negative 1 and negative 1 times 1. Those are negative 2. So all the different combinations are going to work. So at this point, we actually finish without doing anything too fancy here. We can now write our Mulliken symbols. And so for our Mulliken symbol rules, we know that if we have a dimensionality of 1, so the character under E is 1, it's going to be an A or B. How do you decide whether or not it's going to be an A or a B? Has to do with the character under the principal rotation axis. So if you're symmetric, if you're a positive number, you give it an A. If you're negative, you're going to give it a B. And then you just go to, in this case, the next symmetry element, which is negative, which is C2x, we called it. It's arbitrary. And you're going to give it a subscript 1 if it's positive and a subscript 2 if it's negative. Now, you might be asking the question, well, what if I wrote C2y next? Wouldn't my subscripts flip on some of these? And they would. You can see that if I wrote C2y first here, this vector would be called B2, this vector would be called B1. And this is a source of a lot of confusion when looking at homework problems, because there's actually a lot of times with sort of these little bit of a strange point group where you have 3 C2s here. It gets a little arbitrary. There's no real convention for this. So you might see these flipped actually. And we can check to see how it was done in this point group. And you can see here, even the Mulliken symbol rules were a little different. They called this one B1, B2, B3, right? And so, does it really matter in this case? They could say, well, my principal rotation axis, they actually, I don't like this. They changed the definition of the principal rotation axis in order to call these B's. But at some level, it doesn't really matter. So you have to make sure you're talking the same language here. But you can see that they called it B1s through B3s. So Mulliken symbol rules here for this sort of strange point group with 3 C2s aren't really well defined. But what we can also do here is just go through how these different functions, some of these different functions, at least x, y, and z transform, to show you where that comes from. Sometimes we use the functions, we plug functions in to derive the character table. This one we just puzzled out using the orthogonality rules, right? But you could see that if I have an x, y, and z defined like this, I don't even have to draw the molecule or think about the molecule. And now I think about a z vector. Well, if I do identity on the z vector, I'm going to get the z vector back, so that's going to be 1, right? And strictly speaking, what we're talking about here is a 1-by-1 matrix, and taking the character, that's why it's called the character tables, the trace of the matrix, the character, the sum across the diagonals, what's a 1-by-1 matrix. So it's only 1, but that's why we have a value of 1. But for doing this rapidly, z went to z, so we have a positive 1 when we did the identity. The next one here, we have a C2Z. Well, if you do a rotation, right, that's doing a 180-degree rotation that way of a vector like this that is in the z, it's not going to do anything. So that's why you get a positive 1 there. Okay, but now if you do a C2Y, right, a C2Y, that's now flipping this. It's doing a rotation that way. So that's going to flip z into negative z, which is why you get a negative 1. Similarly, if you do a flip that way on the z, that's going to flip things down, and so you're going to get a negative 1. And so what ends up happening here is that anytime you're doing a C2 in the same direction, in the same axis as your function, as your linear function, like y, that's going to leave it unchanged. So y has a +1 there, but then the other ones are negative 1s because that's going to flip it. Of course, identity stays as a +1. And then if we were to look at an x vector, the C2x keeps it unchanged, and of course identity, the other ones flip it. Okay. And Rx and Ry and Rz are very similar, they're just rotation, and those end up transforming the same. And then you can think about the quadratics, right? So, what happens with a quadratic when you do this? Well, it's just a combination of both. So if we take the example of xy, well, when we do a C2z to that operation, x went to negative x and y went to negative y, so that equals xy. So we ended up being unchanged. That's why we have a 1 here for xy. And then if we think about the next one, which is C2y, x went to negative x, y went to y, we're rotating along the y, so nothing happens, so we got a negative 1 there. And then very similar thing for C2x. X doesn't change because we're doing it in the x, but y goes to negative y, and so that equals negative xy, so we get a negative 1. So that's where this comes from. You can do a very similar thing for the cubic functions, right, x, y, and z. If we were to do that, we just add z's here. So z went to z when we did a C2 along the z. So that just equals x, y, z. Y actually went to, for C2y, that's going to go to negative z, because we did like what we talked about over here, where we're flipping that z vector along the y. So that actually ends up being, now you have negative x times negative z times positive y, x, y, z. So we got a 1, and we're talking about this one right here. We did a 1. Identity, of course, is positive 1. And then C2x, now we're doing x, y, z. C2x, again, is going to do a negative z. We're flipping it this way, went from here to here. So it's negative z. So that gets us positive x, y, z. And that's why we have a positive 1. So that x, y, z cubic function, that's the symmetry of one type of f orbital, is totally symmetric. Ones across the board.